Welcome back to the class. In the previous lecture, we were certainly talking about the finite element formulation for a rod element, and today we'll be consolidating on the rod element itself. Okay, so the topic for today will be doing the derivation part, the derivation of equilibrium equations, for the elements, derivation of equilibrium equations for the elements. Now, if we return back to our previous case, we had a rod and we had divided this prismatic rod into a single element. At this point, it was subjected to force. I think it was P. And here it was, we said that the reaction is, say, for example, R. Let's say this point, what we call as a node, is having coordinate x1, and this point is having the coordinate x2. And this rod was also subjected to the traction forces, which we stated as T as a function of x, and the entire length was certainly equal to L. Now, as we move into this case, let's first of all write down today our way of solving this problem, calculating the stress and strain, will be very much different than what we derived in the previous lecture 1. First of all, let's write the principle of virtual work statement for this case. As we write the principle of virtual work statement for this case, it will be, let me use it, it will be equal, or let me change it. So it's equal, we'll be writing, first of all, we write integral from x1 to x2 sigma the virtual strain. If we calculate it in terms of the normal forces, then we don't have to do anything with the stress. So it is, I will be writing here the normal reaction as we have done in the previous case into the virtual strain dx. This is, we are on element 1. Okay, so this is, we'll write here 1. This is also for element 1 dx. We'll also superscript them for element 1 of element 1 dx is equal integral from x1 to x2 for element 1 to x2 for element 1. Traction is T, okay, for element 1 multiplied by the virtual deformation d of x plus del u1 fx at node 1, right, fx1 for element 1 plus delta u2 fx2. Okay, this is the total virtual work for this case. If we assume at x1 we are having force fx1 acting instead of r, that's all same. At x2 we have fx2. Okay, so what will this give us? So we are solving this problem. First of all, we are writing straight away with the we are first of all straight away starting with the principle of virtual work. Okay, now if we look at the principle of virtual work, we need few important things, like we need the strain term, we need the virtual displacement term. These terms should be well known to us. Now we can at least write the virtual displacement statement. The virtual displacement is n1 is a shape function, delta u1, this is the nodal value of the displacement at node 1, so we'll write this as n1 n1 plus n2 delta u2 for element 1. We can do it like this, okay, because we already know that the displacement can be written in terms of the shape function. Okay, now what about this strain? We can write the virtual strain for element 1 to be equal the d by dx of del u. Okay, because we know, as far as the strain is concerned, strain is written as du by dx. Okay, so we are having virtual strain, so we can write this del u. So that will be equal in terms of shape functions, that will be dn1 by dx, and be careful, n1 is a function of x as previously discussed, del u1 plus dn2 by dx for shape function 1, del u2 for element 1. Okay, now let's substitute these values of virtual strain and virtual displacement back into the principle of virtual work statement. Fine. So what it will give us, sorry, let me configure my whiteboard for some time. This analysis is very important, and in most of the cases we have seen some important things missing. Okay, some important things are missing from the textbooks, and that's why there's a little bit of complexity students usually face while they are solving the FEM problems. Okay, but this is the typical mathematics that we are trying to formulate over here. Okay, and it's not going to be ineffective in anyways. Okay, just a minute. Okay, so let me cut it up. Yeah, sorry. Okay, let me return to the top page and start doing it again. So what we will finally get, as we are substituting back into the expression, that we have in hand is integral x1 to x2. So I'm returning to the expression, normal force on element 1, value of the virtual strain dx is equal integral from x1 to x2 fraction d of x and virtual displacement dx plus fx1 del u1 for element 1 plus fx2 for element 1 Let's substitute the value of strain first of all. Okay, so we can write this as, therefore integral x1 to x2. Now we have the strain which we are writing as dn1 by dx, dn1 by dx del u1 for element 1. This is nodal value of the displacement function, okay, plus dn2 for element 1 by dx del u2 for element 1, okay, and we have our neta 1 d of x coming out equal integral, okay, let me write it over here, sorry, let me write it over here, yeah, integral is equal integral going from x1 to x2 t of x for element 1 del u, that is uh, n1 delta u1 plus n2 delta u2 t of x dx plus fx1 for element 1 multiplied by delta u1. How do you write this delta u1? Yeah, it can also be written as n1. Okay, this is fine. We don't have, this is delta u, not delta u1. Okay, so we have to write it as, I'm sorry, this is fx1 delta u1 for element 1 plus fx2 for element 1 delta u2 for element 1. Okay, this is the principle of virtual work statement for this type of problem. Okay, so let's move further and try to assemble the equations. What we can write as, we can therefore write the entire expression as, sorry, we can write this as, we have del u1 state term here, del u1 state term here, so let's take this del u1 out, delta u1 will be taken out. So first of all, we have integral from x1 to x2, integral from x1 to x2. These x1s and x2s are also superscripted to indicate that they have the coordinates within the element 1. So we'll be having dn1 by dx for element 1, yes, plus sorry, minus integral this term, okay, integral going from x1 to x2, and we have in multiplication with n also, so we have to take this into, so it is n neta for element 1 d of x, then we have this term minus integral going from x1 to x2 for element 1 t of x n1 d of x, okay, this is, and we have this term also, if we take it on the left hand side, it will be minus, okay, f x1 for element 1, fine, plus delta u2, sorry, for element 1, integral going from x1 to x2 dn2 by dx for element 1, and for element 1 dx minus integral x1 to x2 t of x, and 2 for element 1 d of x minus fx2 for element 1 is equal 0. Okay, so if we take all the terms on the left hand side, we'll get it like it. Okay, now since we have the terms del u1 and del 2, this term and this term, they are arbitrary functions. They are arbitrary functions, arbitrary values. Okay, so they are virtual displacement which have some value. So from these equations we can clearly state that then the terms which are in multiplication with the del u1 and del u2, those terms are equal to 0. That is, either this term is 0 or this term is 0. Okay, so as we write the values here, we'll be writing therefore integral going from x1 to x2. These equations have a very complicated type of representation, but the illustration is very simple. dn1 by dx eta 1 dx okay, we can okay, let's remove this bracket over here and start writing minus integral going from x1 to x2 t of xt for element 1, okay, or what we had written as n1 t of x. Okay, that's fine. n1 of element 1 t of x dx. Okay, this subscript as t of x or t as a function of x, that's fine, minus fx1 for element 1 is equal to 0, as well as integral going from x1 to x2 dn2 for element 1 by d of x and 1 d of x minus integral x1 to x2 and 2 t of x d of x minus fx2 for element 1 is equal to 0. This is what we get from the previous two equations. Okay, now how do you write this neta as equal to? Fine, we can make a little change straight again to both these expressions. Now we'll be forwarding both the expressions vis-a-vis. Okay, as far as in previous terms we defined this neta, okay, and we stated this neta has something to do with the stress. Okay, and we stated that as far as neta is concerned, neta is a force. Okay, this neta is a force. Neta on element 1 is equal stress multiplied by area. This is how we represented it. It's equal to stress multiplied by area. Okay, and we also stated that as far as the relationship between stress and strain, it's stress is equal to Young's modulus times the strain, and strain is equal du by dx. So as far as your neta is concerned, neta is equal right here, neta on element 1 is equal to Young's modulus multiplied by area multiplied by du by dx. Okay, multiplied by du by dx. Okay, and how do you write this u? You write this u as n1 u1 plus n2 u2, where n1 and n2 are shape functions and u1 and u2 are the nodal displacements. Okay, so we'll make this substitution in these two expressions. Okay, so we will therefore obtain, so as we make this substitution in these two expressions, what we call as um, the previous two expressions, will therefore obtain, sorry, just a minute. Yeah, will therefore obtain, just a minute, let me change the color. Yeah, will therefore obtain integral going from x1 to x2 dn1 by dx, a function of element 1, dn1 by dx, and ea is known as the fluxural rigidity for element 1, ea, because we are writing neta in terms of ea and strain du by dx. Okay, that is dn1 by dx u1 for element 1 plus dn2 by dx. Okay, so dn1 by dx u1 plus dn1 by dx for element 1 ea for element 1 dn2 by dx is dn2 by dx for element 1 into u2 for element 1, entire expression d of x minus integral going from x1 to x2 with superscript as 1 and 2. They are very difficult to write. n1 1 t of x d of x minus fx1 for element 1 is equal to 0. Okay, similarly the second equation will be written as, therefore we will write the second equation as integral going from x1 for element 1 to x2 for element 1, it will be dn2 by dx for element 1 ea for element 1 dn1 by dx for element 1 u1 for element 1 plus dn2 by dx for element 1 ea for element 1 dn2 by dx for element 1 u2 for element 1 and integral dx minus integral x1 to x2 integral x1 of element 1 to x2 of element 1 and 2 t of x d of x minus fx2 for element 1 is equal to 0. Okay, now these two equations we can further write in a very simplified form. We can write both these two equations in the simplified form now. That will be if we write them in the simplified form, Therefore, let me return back. Slide them over here. Okay, let's slide them over here. Can further rub this. Can write these equations as integral. Now this is very important step that we are performing. X1 of element 1 to x2 of element 1, and we'll take this EA out. This is how we'll be writing both the equations now, okay, for element 1. So please pay attention towards this, and curly brackets. The first element we will write dn1 by dx and dn1 by dx for element 1 So this is the first element of our matrix. So we are writing everything now in the form of matrix, both the previous two equations, that is here dn1 by dx previous two equations we are writing in matrix form now. We're writing them in matrix form, okay, and we are integrating. This is a dx, okay. Let's take this entire integral in the curly brackets. Let's enclose this entire in the curly brackets, and it's in multiplication with, because we are having u1 and u2. You can check it that we can write the equations like this, both the equations in the condensed form, integral x1 to x2 into curly brackets n1 n2 for element 1, the shape matrix, t of x d of x. We are actually writing both the two equations together, is equal curly brackets on fx1 for element 1, fx2 for element 1. Okay, this is the very beautiful way of writing both the two equations in a single form, in a matrix form. Now we have this expression on the left side, this expression, this entire expression that we are writing, okay, from here to here. This entire expression we write as, we call this as k for element 1. This entire expression we call as a for element 1, okay. This entire expression we call as f of element 1, and this expression we call as q of element 1. So we can therefore write this entire expression as ka minus f is equal to q. So this is k of element 1, a of element 1 minus f of element 1 is equal to q for element 1. Okay, so if you are asked what is this k is called the element stiffness matrix. So this is the k that we call as element stiffness matrix, and we know what it has. It's an integral of the derivative of the shape functions in multiplication with the nodal coordinates, the nodal values of the displacement function. Okay, so this is called element stiffness matrix, So this is very important. K we call as element stiffness matrix, and A is known as the displacement matrix. Nodal displacement vector or nodal displacement matrix. Nodal displacement matrix. And what is this F containing? F contains the external forces, the external force vector, we can call this as, or it's called nodal force vector. Okay, so we call this as most probably nodal force vector. So this is K minus F into Q. As far as now this Q is concerned, what does the Q represent? It represents the values of the reaction forces at these nodes, Fx1 and Fx2. Okay. Now, if we move forward and try to see what does the K represent, so you can return back to this expression and see what does dn1. Okay, let's take a little bit of time in finding the value of K for a bar element having what you call as having one element. Okay, so we had just stated that this K includes what you call as first let's find the shape function n1 is equal x2 minus x divided by L, isn't it? So if we differentiate with x, so we'll write dn1 by dx is equal minus 1 by L, and as far as n2 is concerned, that is equal x minus x1 divided by L, which implies dn2 by dx is equal to 1 by L. So let's substitute these expressions in this. So we know dn1 by dx, we know dn2 by dn1 by dx. Okay, that's equal to minus 1 by L, this equal to 1 by L. So let's try to find this stiffness matrix. We also imagine that EA is constant and the length of the element goes from 0 to L. Okay, the length of the element goes from 0 to L. EA is constant. These values we know. Therefore, let's try to find the value of K. Okay, so the values of the K will be equal. It will be, the value of K will come out equal. K is equal. K is equal. EA is constant. That will come out of integration. Integral 0 to L. So we have first is dn1 by dx. That's minus 1 by L into dn1 by dx. That's again minus 1 by L. So minus minus will be plus 1 by L. Okay, the second element is dn1 into dn2. That's minus 1 by L into 1 by L. Here it is 1 by L into minus 1 by L, and here it is minus 1 by L dn2 by dx, that is plus 1 by L, sorry, plus 1 by L into plus 1 by L into d of x. So if you solve this expression, the value of the stiffness matrix for a single element bar will come out equal K stiffness matrix for element 1 will come out equal EA, okay, by this is entirely L square. Okay, so this L square will come out. Okay, so this is you'll get L square. Okay, integral 0 to L, then you'll be having 1 minus 1 minus 1 1 d of x integral. So this will be integral 0 to L dx, that's equal to L itself. So the total expression will be equal to EA by L for element 1 into 1 minus 1 minus 1 1. This represents the stiffness matrix for a rod element. Okay, so this is very much well known in these equations, in very much well known in what you call as the fundamental books of the finite element analysis. Okay, so this is how we write it. So this is ea by l for element 1, 1 minus 1 minus 1 1. Okay, this is stiffness matrix. And let's try to see the f matrix, small f matrix. Okay, okay, so as far as a small f matrix is concerned, we just stated that small f matrix was equal integral going from x1 to x2, and then it was n1 n2 for element 1 for element 1, and t of x dx. Okay, t of x is traction. So what is n1 equal? N1 is equal, if we substitute the value of n1, okay, and it will be integral, since our x1 is 0, x2 is l, is n1 is equal to x2 minus x divided by l, and this is x n2 is equal to x minus x1 divided by l. Let's suppose the traction is constant traction, it is subjected to t of x. We have a d of x. The values of x2 and all are constant. Okay, therefore this entire expression can be solved when you write okay, let me solve it for you people, so that we get the final shape of this matrix. It will be like, with we know x2 is equal to l, and with our x1 equal to 0, so it will be our force vector for element 1 will be integral 0 to l minus x by l, and this is x by l. T of x d of x, which therefore can be written as, let me rub it up, which therefore can be written as, let me clean some space, this can be written as f1 for element 1 will come out equal, this is l minus, this will be, let me write it, traction is, let me assume the traction is constant, so that t will come out, this is equal, this is integral l d of x, that is l, and integral, so that's l square, minus this is x square by 2 from 0 to l, that is l square by 2 divided by l, and the value of this will be l square by 2, and you have your l, so that will be equal t, this is l square minus l square by 2, that's equal, that's written in the form of curly brackets, l by 2, and here it's also written as l by 2, so this can be written as tl by 2, and in curly brackets we'll write 1 and 1. So this is how these brackets are written. So how are we writing these brackets? Sorry, how are we writing this stiffness matrix? I will write here K. First of all, the elemental stiffness matrix K is written as K is equal AE by L for element 1 into matrix 1 minus 1 minus 1 1. And how do we write the force vector? Ka minus F is equal to Q. F is it as L T by 2 for element 1 multiplied by 1 1, and it's written in curly brackets. This is the matrix representation of our equations. Okay, this is our K, this is our F. Fine. Now this is very much simple, very much equivalent to what we have already done. Okay, so we'll continue from here in the next class. Thank you.